thank you. So now I'm going to show how to apply this very nice hydrogen process, annealing process, to the silicon photonics platform of Leti. So we have developed this silicon photonics platform for a variety of applications for the last few years. And I will start by introducing the platform from a technological point of view. I will show you the results we obtain in terms of propagation losses for the waveguides and what is the impact on the devices that we have on this platform. Okay, so let's start with the platform. Still not. Okay. So this is a view of the silicon photonics platform. So starting material is silicon insulator 300 nanometer. I will focus here on the 200 millimeter platform, but we have also a 300 millimeter platform in wafer size, which is very similar. So you have a cross section at the bottom of the slide of the platform, and it's organized as several building blocks. So the first one is the silicon patterning, and we have 3 levels of silicon patterning. We have dopings to make PN junctions for modulators. We have germanium to make photodetectors. We have the possibility to have a silicon nitride waveguide for some passive components. We have a heater to be used as a phase tuner, and a 2-level back-end offline for metals. We have also the possibility to integrate 3-5 hybrid lasers. You have on the right side of the slide some pictures, SEM picture of some of the devices that we can make with the platform. So for example, a 2D grating coupler, a stack with silicon and silicon nitride, a ring resonator that can be used as a modulator, MMI. So as part of this platform, we offer photonic design kit, PDK, and we can offer some runs through multi-project wafers. And we target on applications like Datacom, telecom, sensors, but also alternative computing. Okay, so let's see now the results. So when we apply this hydrogen annealing to the full platform, and we target very low loss, propagation loss for all the type of waveguides that we use. So the strip and rip waveguide, you can see the cross sections here, already mentioned by Erwin, but also the deep rip waveguide with a thinner slab that is used in the Mach-Zehnder modulators as a good compromise between optical modes, confinement, and electrical access. So we want to have low loss, of course, but we want to make sure that passive components that we already developed on this platform, so for example, grating couplers, all type of transitions, are still working after the annealing, and that the active devices too, for example, the Mach-Zehnder modulator is still working. It's very important for us that by applying this process, we don't have to change the design of our components. So you see on the right side the cross-section of the waveguides without the smoothing, and now you see it. Okay. Now you see the cross-section of the waveguides after the annealing. So again, we can see that the shape is preserved by the annealing. It's not the same. The corners are a bit rounded, but the overall shape is preserved. And it's also thanks to silicon nitride hard masks that we have on top of the silicon. Okay, so let's see now the results in terms of propagation losses. So in the plot here, on the top left of the slide, you have the results of the different types of waveguides, the propagation loss measurements for waveguides rib, strip, and deep rib in both spectral bands that we are interested in. C band, so around 1550 nanometers, and O band around 1310 nanometer. And the loss reduction by applying the annealing treatment is really spectacular. So for example, for rib waveguide in C band, we go from 0.7 dB per centimeter without annealing to 0.1 dB per centimeter with the annealing. For strip waveguide, we go from 2 dB per centimeter without the annealing to 0.7 dB per centimeter with annealing. So we have a very good improvement of propagation losses. It's even more impressive, for example, for strip waveguide in the O band, where we go from 3.5 dB per centimeter to 1.1 dB per centimeter. On the right side of the slide, you have some mapping of the propagation loss. So at the wafer scale, so it's a measurement at the wafer scale. And you can see that the value that I give here, for example, 0.1 dB per centimeter for read waveguide, it's the median value over the wafer. So it's not the lowest value, it's the median value. And the standard deviation of the wafer is very good too, with, for example, here 0.04 dB per centimeter for read waveguide. On the bottom side, it's for strip waveguide, so it's very uniform too. 1.1 dB per centimeter for the median value and 0.2 for the standard deviation. So it's a very good result in terms of propagation loss. So it means the process is very efficient to reduce the roughness of the smoothing of the sidewall. We have very good wafer universality, and we are better than what we can obtain with immersion lithography patterning. So those results, for example, 0.1 dB per centimeter in the C band and 1.1 dB per centimeter for strip waveguide in the O band, are at the state of the art in terms of propagation loss. Okay, so I told you it's important for us that we can preserve the performances of the passive devices. It's difficult to change the slides. Okay, so this slide to show you what happens when we apply the smoothing and annealing on the two devices, which are quite important. So the first one is a grating coupler. So it's very important to have a good grating couplers to couple light in and out of the chip. And one important parameter is the central wavelength of this grating coupler. And we target, for example, 1310 in the O band. And you have a mapping of this central wavelengths measured on a wafer after annealing. And the median value is at 1314. So for us, it's very good. That means that we don't change much the central wavelengths, and means we can still work with the wafer with this after this annealing. In terms of insertion loss, it's very good too. We have 2 dB loss for grating. The second device is a directional coupler. And again, you can see by comparing without smoothing and with smoothing annealing that the transmission as a function of the gap between the two waveguides is steady. Okay, so now let's have a look to active devices. So the Mach-Zehnder modulator, that is very useful in the platform. So I just put some examples of high-speed modulation. For example, NRZ, we obtain 64 gigabit per second, and in PAM for 28 gigabaud. So we do the dopings, we make the p-n junctions before the annealing. So we want to be sure that with the high temperature of the annealing, we don't change the shape of the p-n junction. So on the plot at the right bottom side of the slide, I compare a wafer without annealing, this is a blue dot, and with annealing, the orange dot. And I plot the insertion loss as a function of the efficiency, which is V pi L pi here. You can see that the efficiency is not changed with the annealing. It's still 1.6 volt centimeter, but the insertion loss is reduced. So we improve the insertion loss of the device, and we don't change the efficiency. So it's very good for us. So for example, in this circuit, taking into account the active part, which is 1 millimeter long, and the routing section, we have a gain of 1.5 dB on the device. So it's very interesting for the circuits. Okay, so this is a conclusion. So we applied this H2 smoothing annealing to reduce roughness of the waveguide. We have very, very good results in terms of propagation loss. We have the state of the art in terms of propagation loss at 1310 and 1550 nanometers. So 1 dB per centimeter for strip and 0.1 dB per centimeter for the waveguide. And the components of the Photonics library have the same performances with this process. We don't degrade the performance. We have several dBs of power gain in complex circuits already. And I'd like just to say a few words to highlight some results in quantum photonics. So for quantum photonics, the low propagation loss of waveguide is really essential. First, for the generation of the photon pair that we do in microresonators. So we need high quality factor microresonators to make those photons pair. And then we need to manipulate the single photons in complex circuits. And we don't want to lose the single photons on the way of the circuits. So it's important to have this very low loss. And we already have some first results demonstrating the generation of photon pair using this technology. And this ends my presentation.
Okay, thank you, Quentin. Thank you, Erwin. We have time for one question from Jean-Pierre, who is asking what would be the typical cycle time for an MPW run. I just can mention that we have developed with Mentor Graphics design kit using Tanner 8 Suite, and so things are easier for us if the designers use this design kit. And the typical cycle time from the tape out to the silicon out is less than 6 months for the platform that has been shown by Quentin and Erwin.